This video is on the section 8.5 notes, inequalities and systems of inequalities in two variables. So when we graph an inequality, we're going to have infinitely many points that are on the line and not on the line that make that inequality true. So these points are represented on the line itself or the curve itself if we have a solid line, and they are non-solutions if we have a dotted line. The points that are off the curve, and you'll see what I mean in a second, are denoted by shading in the open space. So when we have solutions of inequalities, we know that if we have a less than or equal to sign or a greater than or equal to sign, then the points on the line will be solid and they will make the equation true because we will have an equal to sign. So the left side and the right side will be equal to each other and it will be true. If we don't have an equal to, then we're going to have a dashed or a dotted line because the points on the line will not work in the inequality itself. And then open spaces will be shaded if they're solutions. Open spaces will not be shaded if they're not solutions. So this first part should be a review from high school, but I'm going to go through it anyway. So first it says to graph these linear inequalities, and so this is in y equals mx plus b form. I'm just going to start with my y-intercept of 3, and I have a slope of 1, and I can write that as a fraction by putting 1 over 1. And so I'll just go up 1, right 1, up 1, right 1. Now when I draw the line, there's no equal to, so I'm going to draw a dotted line, because all the points that are on this line will make the left side and the right side equal to each other, and it says we can't have them equal to each other. So the points on the line will not be considered solutions. And then with inequalities, we either have shading on one side of the line or the other side of the line, and that shading represents points that would make the inequality true. And so to figure out what side to shade, you just pick a point to plug in and you see if it's true or false. If it's true, you shade on that side. If it's false, you'll shade on the opposite side. And there's no specific point you have to pick. You could do a different point every time, but most people use 0, 0. And we do that because we're lazy and it's the easiest to plug in. So if I have y is greater than x minus 3 for my inequality, and I plug in 0 for y and 0 for x, then I get 0 is greater than 0 minus 3, or 0 is greater than negative 3. And this is a true statement. So that means that where the point is true, the other side is false. And so I'm going to shade over here. So plugging in 0, 0 was true. I could plug in 1, 1. 1 is greater than 1 minus 3. 1 is greater than negative 2. Any point over here would make this inequality true. Any point over here or any point that's on that dotted line, if I plug it in, would make the inequality false. All right, let's try this next one. So I'm going to go ahead and get this into y equals mx plus b first. So I'm going to move the x over to the right side and then divide by negative 1. And so I'm going to start at negative 1 and do a slope of positive 2. So up 2, right 1, up 2, right 1, up 2, right 1. And then this inequality says equal to. So when we have points that make the left side and the right side equal each other in the inequality, they will be solutions. They will be true. So solid line, and then again I'm going to pick a point to plug in, a point that's on one side of the line or the other to see where I should shade, and 0, 0 is a good point to use because it's clearly on one side of the line. So 2 times 0 minus 0 is greater than or equal to 1. 0 is greater than or equal to 1, that's false. And so this side is the false side, it should not be shaded. That means that this side is the true side, and it should be shaded. X plus y is less than 0. I'm just going to solve this for y. So y is negative x is the line that I'm drawing. I have a y-intercept of 0 and a negative 1 slope. So down 1 over 1, down 1 over 1, down 1 over 1. I wanted to do this specifically so that for one of these example problems, we could not plug in 0, 0 as our test point for our shading. So this one, we can't use 0, 0 to decide where to shade because 0, 0 is on the line. And so you wouldn't know where to shade if it was true or false. We know 0, 0 is going to be false because this says less than. It doesn't say less than or equal to. So this is a dotted line, and the points on the line are not solutions. So I can pick any other point to plug in as long as it's not on the line. And if 0, 0 doesn't work, then usually I will pick 1, 1. And again, I pick it just because it's easy to plug in. So x plus y, 1 plus 1 is less than 0. 2 is less than 0 is a false statement, so this would be the false side, and that would make this side the true side. All right. Last, this one is still a linear equation, but it's only in one variable, which means it's a line that is not slanted. So this says y is less than or equal to 3, which means that the y-coordinate of every point on that line is a y-coordinate of 3. So we have the point like negative 4, 3, negative 2, 3, 1, 3, 5, 3. That's how you make a line where the y-coordinate is always 3. I'm going to draw a solid line because this says equal to, so the points on the line are solutions, they are going to work. And then again, I can just pick 0, 0 to plug in because it's easy to plug in. There's no place to put an x-coordinate, but I know that the y value is less than or equal to 3. 0 is less than or equal to 3 is true, and so I'm going to shade on the bottom side of the line because that's where the solutions are. All right, now I can go ahead and move to the next page. So this is something you probably didn't go over in high school. This is graphing inequalities, but graphing inequalities that are not straight lines. And it works basically the same way that a line would. With a line, you started off by graphing it dotted or solid, and then you picked a place to shade that was either on one side of the line or the other side of the line. And so we're going to do the same thing for these curves. We're going to draw the curve first and figure out if it's dotted or solid, and then we're going to figure out if we should shade on one side of the curve or the other side of the curve. So here we have y is greater than x squared. I know that x squared has these points if I go back and look at the table for my parent function. And so I'm going to go ahead and graph these points. There's my quadratic, and I know from the symbol that it should be a dotted line, not a solid line. And then because of the shape of my graph, I'm not going to think about the left side of the line and the right side of the line, or the bottom of the line and the top of the line. I'm going to think of this as the inside of the parabola versus the outside of the parabola. And that's how I'll determine where the shading should go. So I can't use 0, 0. I can't use 1, 1. Another point that would be easy to plug in, I tend to like to plug in positives just so that I don't make a mistake with negatives. But you can really plug in any point you want. So I'm going to use 3, 1. I'm going to plug in 1 for the y value and 3 for the x value. 1 is greater than 9 is false, and so I'm not shading the outside of the parabola, I'm going to shade inside the parabola. This next one is a circle. I can tell it's a circle because it says x squared plus y squared, so this is a circle that's centered at 0, 0. And then it equals 4, which is the radius squared, and so that means that this has a radius of 2. So I'm going to go a distance of 2. in each direction. This problem also says equal to, well, not also, that one was dotted. This one says equal to, so I'm going to go ahead and draw a solid line here. And then the circle does not go through 0, 0, so that's a good point to plug in. So I have 0 squared plus 0 squared is less than or equal to 4. And that's true. So in this case, with the circle, I have inside the circle versus outside the circle. The point inside the circle is true, and so I will shade inside the circle. All right, next we have a log graph. If you remember when we graphed the log graphs, we always had 2 points that we would start with. So our first point is 1, 0. Our second point is our base and then 1. And the base here is 2. So 2 and then 1. And then we always had a vertical asymptote for log graphs of x equals 0. So I'm going to start off by drawing a sketch of my graph. Here's my vertical asymptote. And then I've got the point 1, 0 and the point 2, 1. And based on this symbol, I know that I'm going to have a dotted line. Now, if you run into a problem where you have an asymptote in the problem, you have to figure out which side of the asymptote the curve is on. And so the curve is on the right side of the asymptote. That means the left side of the asymptote can't be shaded. There can't be any solutions over there, and I know that before I even consider where my shading should be, because asymptotes don't get, in this situation, they don't get crossed. There aren't solutions over here that can be plugged in to this function and be considered true, because these numbers, these negative x values, don't work. You can't take log of a negative number. So these, no matter where the shading is, it won't be over here. Now, to figure out the shading, I'm going to have above the curve and below the curve. I can't plug in 0, 0 because that's on the asymptote. So I'm going to go ahead and plug in 1, 1. 1 for y, 1 for x. 1 is greater than log base 2 of 1. And log base 2 of 1, if you don't remember off the top of your head, you can just plug it into your calculator. Log base 2 of 1, it's actually 0 because you're saying 2 to what exponent gives you an output of 1, and so this would be 0. 1 is greater than 0 is true, and so we're going to shade above the curve. So I've got all this right here is shaded, and then I'm going to shade all this in here in between the curve and the asymptote. So all this little bit gets shaded. Like that. All right, next we're going to look at systems of inequalities. A system of inequalities would be an inequality or a system where you have 2 or more inequalities to graph. So we're going to have 2 lines or 2 curves, or maybe even 3 or 4 or 5, where we have a dotted or a solid line and some shading, and then another dotted or solid line, and then some shading for that one. And so our solution to the system is going to be the places where there are solutions for the first one and the solutions for the second one, and they overlap. And they're not going to overlap at a single point usually. They're going to overlap in their shaded areas. They could also overlap with 2 solid lines intersecting, so you could have some specific points in there that you can see, but most of the time we're looking at that double shaded area, or if we had 3 it'd be triple shade, or 4 quadruple shade. So a system of inequalities, because we have shading that's overlapping, they almost always ask you to shade them graphically or to solve them graphically by shading. You won't be given an inequality and asked to solve it and not be graphing it. So I'm going to go ahead and do these first two inequalities and solve this one. This again is pretty much like high school. There's no difference between what you've learned before. So I'm going to start off by writing this equation down so that I can get it into y equals mx plus b form and make it a little bit easier for me to graph. So y is negative 1/2 x plus 2. Start at 2, and then go down 1, right 2, down 1, right 2. And the symbol here tells me I should be drawing a solid line because it says equal to. And I'm going to plug in 0, 0 to see where to shade. So 0 plus 2 times 0 is less than or equal to 4. 0 is less than or equal to 4 is true. So I'm going to shade this way because that's where 0, 0 is. Okay, and when I do these, I usually do them a little bit lighter because I know I'm going to have to shade more than one time, and I want to see where the shading will overlap. So next we have a straight line with a y-intercept of negative 3 and a slope of 1. So I'm going to go up 1, right 1, up 1, right 1, up 1, right 1. And this is a solid line as well. And then again, I'm going to plug in 0, 0 to that inequality and see if it's true or not. So 0 is greater than or equal to 0 minus 3. 0 is greater than or equal to a negative is true. And so for this line right here, I'm going to shade above and to the left. And when I do systems like this, I like to have the shading for one and the shading for the other. I draw it different directions so that it's really easy for me to see where my overlap is. And then to make sure the person looking at my paper is not confused at all, I go in and I make this darker. So you as the person doing the problem might be able to keep track easily of your double shaded area, but somebody coming in to look at your paper might have a hard time. So always go back and make the double shaded area extra dark. So what this means is that this whole area is where the solutions are that make both of the inequalities true. And you can use this point where the two lines cross. You can use any point on this solid line, any point on that solid line, any point over here, and they would make both inequalities true at the same time. Any points over here, over here, over here, they wouldn't work. They might make one inequality true, but not both of them. All right, let's go to the next page. So here is another problem, but instead of having a system of straight lines, we're going to have a system of two curves. So I'm going to start by drawing this one. X squared plus y squared is less than or equal to 16. That's a circle centered at 0, 0 with a radius of 4. And it says less than or equal to, so that means I'm going to draw a solid line. All right, and I'm going to plug in 0, 0 to see if I should shade that curve inside the circle or outside the circle. So 0 squared plus 0 squared is less than or equal to 16. And that is true. So I'm going to shade inside the circle for that one. Over here we have an exponential equation. And I know with exponential equations that the points that I use are 0 and 1, 1 and the base. And then I know I have a horizontal asymptote at y equals 0. So I'm going to go ahead and graph that. Horizontal asymptote at y equals 0. The point 0, 1 and the point 1, 2. And then this curve does not have a solid line, does not equal to, so I'm going to draw this with a dotted line. So I know for this exponential graph, I'm not going to have my shading cross the asymptote. So I'm not going to have any shading down here at all. Except for the shading in the circle. That shading can still be true for just that inequality. It just won't be true for both of them. And then now what I can do is plug in a point to my exponential inequality and see if I should shade above the curve or below the curve. And I'm going to go ahead and use the point 1, 1. I cannot use 0, 0 because it's on the asymptote. So I'm going to use 1, 1. Y is greater than 2 to the x. This is false, and so that means that I'm going to shade on the other side. So I'm going to shade above the curve since that point was below the curve. And then my solution to the system is going to be this double shaded area, and so I'm going to go in and make this area extra dark so that whoever's looking at my paper can see exactly what I meant by my solution. So this solution is interesting because we do have a solid line and a dotted line. So here, where the solid line and the dotted line cross, is not a solution. It would work in one inequality, but it would not work in both of them. None of these points on this dotted line are going to work. Where this dotted line crosses the solid line, that is not a solution. Now, any point that's in here in this double shaded area, those points will work in both. The points that are on this solid line right here will also work in both as long as we're not talking about the intersection. So from here to here, all these points are good, all these points are good, but this dotted line we can't use. All right, we've got one last example. We're going to do a system of inequalities that has 3 inequalities involved, and it's going to be the same thing we just did, but we're going to have 3 shaded regions overlapping instead of 2. So I'm going to start with my quadratic 0, 0, 1, 1, 2, 4, 3, 9 is off the graph. You could draw it up here if you wanted to. 3, 9, negative 3, 9. That's a dotted line. I cannot plug in the point 0, 0. I cannot plug in 1, 1. So I'm just going to choose a point over here that's easy to plug in. I think I did 3, 1 last time, so I'll do that again. 1 is greater than 3 squared. This is false, and so that means I'm shading inside the quadratic. And then we have 2 solid lines after that, 2 straight lines after that. So I've got a y-intercept of 6 and a slope of positive 1, up 1 over 1, up 1 over 1. And this says to draw a dotted line. And for this line, I could use the point 0, 0 because it's clearly below the line. So I'm going to go ahead and use that point. 0 is less than 0 plus 6. 0 is less than 6, which is true. And so I'm going to shade this way. And then for the last one, starting my line at a y-intercept of 6 and drawing a negative 1 slope. So down 1 over 1, down 1 over 1. Again, we have a dotted line. And since 0, 0 is clearly on the bottom side of the line, I can go ahead and use that to see where my shading should be. Negative 0 is still just 0. So 0 is less than 6. And so for this line right here, I'm going to shade towards 0, 0. And you can see that when I had 3 shaded regions on this one, things got kind of convoluted. So one trick to doing these problems is to use colored pens or colored pencils and to do each shaded region in a different color. And then your answer is where all the colors intersect each other. All the colors are on top of each other. So I kept track of this. I can see that this bottom part of the quadratic is where we have this triple shaded region. So especially when I have 3, I'm going to go through and darken that area so it's really easy for people looking at the paper to see exactly where the solutions are. And then here we had all dotted lines, and so this intersection, this intersection, this intersection, none of those are solutions. None of these points on the edge of the shaded region are solutions because all of them are dotted lines. But we do have solutions in here in the shaded region.